See, that one was a little more hidden, wasn't it? Okay. So this becomes a new integral. I have this right here, 1 over 9 plus u squared. 1 over 9 plus u squared times e to the x dx is du. That looks a whole lot like what? There was one that I told you to remember. Arctangent, right? The arctangent one, except the arctangent, didn't it have a 1 here? Yes? Not a 9? So please refer to your formula sheet now, because if you look at the formula number 17, it's a more generalized formula for arctan. Formula number 17 says that if you have an integral 1 over a squared plus u squared du, do they put u squared in front of a squared? It doesn't matter, it's addition, it can be either way, right? That the antiderivative of that would be what? 1 over a arctangent of u over a plus c. Now, what the formula I gave you, what was the number I had here in the formula I gave you when I first introduced you to it? It was 1, wasn't it? And that means that a would be 1. And that means this is 1 over 1, which is just 1. And this would be u over 1, which is just u. So that's why if this is a 1, it's just arctangent of the variable. But this is more general. If you have another number here, you can actually deal with it. Well, no, it doesn't even have to be a perfect square. So like if your number, if this right here, we're going a little off topic, but if I had this, I could still do that because a would just be the square root of 5. Right? Because what number squared gives you 5? Square root of 5 gives you 5 when you square it. So this does not have to be a perfect square. A lot of times it is because they like to keep the numbers clean, but by no means is that necessary condition. Right? Yes? Okay. All right, so according to this formula, this will be equal to what? 1/3, because a is 3. Arctangent of u over 3 plus c, and then replace u with e to the x. And we're done. I think it's time for you to try one. You can do it.
Would it matter if we use positive 3 or negative 3?
Where?
For the square root of 9.
That's a good question. No, it'll be, does the formula have absolute value or no? It doesn't. No, it'll be the principal root, so it'll be the positive one. You have to use the principal root. All right, so how about I'm going to give you 2 to work on, all right? One of them will be kind of easy. The other one will be a little bit harder, all right? So let's see how you do. Y'all can work together if you'd like. First one, integral 5 plus 2x to the 7th over square root 40x plus 2x to the 8th dx. The next one, so we'll call this problem A. Problem B is integral sine 2x over 4 plus cosine squared x dx. I'm going to give you about 10 minutes to see how far y'all can get with those two problems. All right? You're free to help each other out, work with each other.
Divide that by 8.
Absolutely. That's exactly what you want. Mm-hmm.
40x plus 2x.
What you got? Did you divide by 8? Yeah. Okay. So you wondering what to do with this?
I was just stuck. I
Okay.
kept going yet.
Yep. Just remember your integral sign. Keep track of everything. Back here? How about on the first one?
Yeah, that's what I'm doing.
Okay, so do you see something? Okay.
So I pulled out. Choose this.
Yeah, because the derivative, that's a 7th degree. You have 40 plus, so you take the derivative. Go ahead, you scratch it out, but write it down again. Write down that derivative again.
So I take the derivative of this.
Uh-huh.
Plus 40.
Uh-huh. And then put dx behind it. Throw it in parentheses because it's the 16.
Gotcha.
Yeah, and then make that equal du. So du in front of that. Okay, so that's what you have.
Yeah.
So you look up, and what you have up top needs to somewhat match that over there.
Okay. So I just have to make it look like this.
Yeah, can you? Is there a way you can do it? What is the number you need in front of the x to the 7? For it to match, you need it to be a what? Like you have 16, what do you need it to be?
I need it to be 2.
A 2.
8.
So you'd have to pull an 8 out of there. Can you pull it out of both?
Yeah.
Okay, so just factor an 8 out of both sides. So put du equals, pull an 8 out.
Okay. I have what?
Yep, dx. Now, do you see that 2x to the 7 plus 5 dx
So it'd be
matches
1/8.
1/8? There you go.
Awesome. Thank you.
You got it?
Yes, sir.
Okay. So you can pull an 8 back there. Yes. So that was u. This one is u to the negative 1/2. There should be a constant. You lost a constant somewhere in there. I think you were good up to this point.
Yeah,
Right.
that's the 2.
So, right, this was the 1 over square root. So when you add 1 to that, then you do the little thing in front, flipping. You're gonna pick up a number there. Yeah, that's the only issue I saw there. How are we doing here at this table? Anybody have any? Getting the first one?
Yeah.
Yes. How about you? Okay. So you got your derivative. When you took your derivative here, you put a 40x, yeah. So when you took the derivative, I think that might be the issue. When you take derivative of 40x, you get 40.
Oh, that's fine.
Right? And then at this point, yeah, and then 16. There you go, the 1/8. You see how the 1/8 will make it look exactly the way you need it? Yeah. All right. So you got. Did you get the first one?
I think I'm getting
Yeah. Now you divide by 8. Okay. Yes, you're on your way. How we doing? Did you try something for the first?
I did. I put a u for the 40x.
Plus 2. The derivative of that was 40 plus 16x squared.
I'm having trouble factoring that.
Okay, so you have this, right? You have 40 plus 16x squared dx, right? That's what you have. And what you want it to be, it would be really nice if it was a 5 plus 2x to the 7. Sorry, to the 7. That's what you have, right, as your du? Let me just double check it, right? That's what you got. So you would really like this to match up with the 5 plus 2 to the x to the 7. So notice that these both have an 8 that you can factor out. So if I pull an 8 out, 8 times 5 is 40. 8 times 2 is 16. Do you see that? And then this matches what's up there on the top, so you just divide by 8 on both sides. So it's a little bit hidden in there. You have to be careful with it. Yep. So it was, be careful here, that's u to the negative 1/2, because it was on the bottom, right? So when you bring it up, it's negative 1/2. All right. I'm about to run through these, okay?
Sorry, I'm still on A, but I got to here. Does that look correct? Am I going the right direction?
This is okay, but not sure what you're, okay, this is okay, this is okay. Not sure what you're doing here.
I think I was trying to plug it in.
You have to find the antiderivative of this right here.
Okay,
Yeah,
sorry.
that's the same as u to the negative 1/2. All right, I'm going to run through these, all right? Let's do this first one. I think most of you chose the u to be the 40x plus 2x to the 8th. And then when you take the derivative of that, you get 40 plus 16x to the 7th dx. And you're trying to see if this somehow can appear up here somewhere. And it took a while for some of you, but I think now most of you are on the same page, that if you factor out an 8 or divide this side by 8, then you get that exactly. And so that means you'll wind up putting a 1/8 on this side, and then this will become exactly the 5 plus 2x to the 7th dx. And then you have to rewrite the integral. And I saw some of you getting a little hung up on this part. When you rewrite this integral, this entire piece right here is going to become what? 1/8 du. So I'll pull the 1/8 out and I'll slap the du on the back. And then what's left is this square root of u, but it's on the bottom. So 1 over root u is the same as u to what power? Negative 1/2, right? That's the same as 1 over the square root of u. Then you have to use the power rule on that to get the antiderivative. So the antiderivative is 1/8, and then u, going to add 1 to this power, so that gives me positive 1/2, and I put 1 over 1/2 here, which is the same as 2 plus c. And then that's 1/4, right? And then what's u? All that stuff, right? 40x plus 2x to the 8th, but all of this to what power? 1/2, or square root. You could write square root, that's fine, plus c. And that's your answer. So just be careful on that. That's a negative 1/2 here, not a positive 1/2. The next one, I'm not sure if anyone got to this one or not. You did? Okay, so you had what? Sine 2x over 4 plus cosine squared x dx. So you got it? What did you use for u?
4 plus cosine squared.
The whole denominator?
Yep.
Okay, so u is equal to 4 plus cosine squared x. Then the derivative of 4 is 0. This we have to use chain rule. So 2 comes out, cosine x, times the derivative of cosine, which is negative sine, so I'll put the negative out front, sine x, and then we slap that dx on the end. Now Ron is telling me that he did this because, and he said it worked. I haven't asked Ron why he did it, but Ron, I don't see the derivative sitting up there, but apparently you do.
Sine 2x is equal to 2 sine x times cosine.
That's right. So you had to know that double angle formula from pre-cal.
Yeah.
Yes.
I remember
You remembered it
with
with a little help of the formula sheet. But at least you kind of remembered something with that, right? So a very important formula from pre-cal was this one. Sine 2x is equal to 2 sine x cosine x, the double angle formula for sine. So anytime you see sine 2x, it can always turn into this. And look at, that's this right here, right? This piece right here. And that's exactly what we have here, but we're off by what? A negative. So I just divide both sides by -1 or multiply both sides by -1. So negative du is equal to 2 cosine x sine x dx. I hope everyone sees what I'm saying. This right here, forget it's there and just put that there instead. And then they match up. So if that's the case, then when I rewrite this integral, the 2 sine x cosine x dx, that whole thing is going to be replaced with what? Negative du. So I'll do it this way. Here's the negative. It's like a -1. The du I'm going to put out here in the back. And then I still have the 4 plus cosine squared x, which is the u, right? But it's on the bottom, so 1 over it. And now we better know how to do that, right, if we're going to be able to do it. I mean, going. This is natural log. So this is negative, because the negative out front. Natural log of absolute value of u, which, yeah, I'll do that next step. That's this, right? Then we will replace the u with what u is in the problem. So this is equal to negative natural log of, what is it? What was our u? 4 plus cosine squared x plus c. And that's it. Now I'm going to show you something the book, like if this were a problem in a book, they might have this as the answer. And my question to you would be, what did they do? What did they do? How does this become this? So you have to go back to this property. Remember this property. Natural log of x to the n is equal to n times the natural log of x. The property of logs from college algebra says that if you have x to a power inside of a log, the power can come out front and become a number in front. It works the other way around. If you have a number out in front of a log, you can move it up as a power. So what we basically did is we took this negative, or they took the negative here as a -1. They moved it up as a power right here, -1. And when you have something to the -1, it basically drops it down. So that you took this whole thing and dropped it down, and it became 1 over it. So the negative goes away in front, and it creates this fraction. Just be aware of that, because books, answers in the back of books, they love to do things like that, and you're like, what the heck? Okay. So look, your only hope in getting good at this is to keep trying problems and doing as many as you can. So the homework for this section, did I give you homework? Let me see what it says here. Oh, no, there's no homework? I didn't write it down anywhere, did I? Okay, so I'll tell you what to do. So this is off of page 252. And you should do 15 through, oh wait, no, this is not the right page. That's the last section, hold on. It's like, what? Section 5.5. I'll give you the same homework assignment as last time. All right, so you should do page 306. 1 through 36. Yes, all. All. So what I suggest you do is start with the odds, knock out the odds so you can check your answer in the back of the book. And then start working through the evens. All right? That's a lot of work right there. But I guarantee you that if you put an honest effort into this, and when you get stuck, you go get help, or you go to the tutoring lab, meet up with a group of people, y'all work on them together, whatever. If you work through these problems, you'll be at least in the game still. If you are struggling with these two quiz problems, these two problems I gave you just now, if you're struggling with those, then if you do no homework, this is going to be an impossible task. You have to practice. All right? So please, come reach out to me, get help. But we're moving on. I don't have a lot of time, but I want to introduce the next topic. Now, I'm not trying to rush you, okay? Don't get the impression I'm trying to like rush through this. I told you earlier, like another class in the past, a past class, what did I tell you? I was trying to kind of move quickly. The harder stuff's still to come, and I don't want to be trying to rush through that. So for most of you who have taken Cal 1, a lot of you had seen this. Let's do a show of hands. How many of you had seen substitution before? Show of hands, okay? How many of you have seen integration by parts? So a few, like 2, I see 2. So integration by parts, this is going to be brand new for most of you. All right, so this is a new formula, a new approach. It's different than substitution, extremely powerful, but you got to know when to pull this tool out. You don't do it for everything, all right? So the way I'm going to introduce this, I'm going to talk through what this is saying here in a second, but I think I'm just going to write it down on the board. Do you remember from Cal 1 that if I had, let's say, 2 functions, I'm going to call one of them v, I'm going to call one of them u. So these are 2 functions. This is a function of x times another function of x. But instead of calling it f of x and g of x, I'm going to call it v and u. Is that all right? Yes? Okay. I could also have written it this way, u and v, right? Either way, multiplication doesn't matter. In Cal 1, we learned that if you take the derivative of a product, right, we have to do the product rule, right? That little mark means derivative. So it would be, what, u prime v plus v prime u. And I think we already discussed how different people learned it different ways, but it's all the same, right? Everyone agrees with this? That's the product rule from Cal 1. This new formula, integration by parts, builds off of this, actually uses this to figure something out. So look at what I'm going to do. I'm going to take this product rule. We got it from taking the derivative. I'm going to come in on both sides of the equation right now, and I'm going to undo the derivative. So if I undo the derivative, what I mean is find the antiderivative. So what is the antiderivative of u times v, like this? And then over here, the antiderivative of this, and then plus the antiderivative of this. So do you see what I've done is I've taken the product rule and I've taken the antiderivative of both sides. On the right side, I can do antiderivative of each one because it was a plus. I can do that, right? Understand? All right, so this right here is an eraser, right? If I say, hey, take the derivative of this eraser and then undo that, what am I going to be left with? The eraser, right? So it's like, take the derivative and then take the antiderivative, then it just comes out unchanged, doesn't it? So the left side of this equation becomes u times v. Agreed? Yeah? Okay, u times v. So the left side is u times v equals, now the right side, I actually cannot tell you what the antiderivatives of these are because these are products, right? I can't split these apart. I'm not allowed to do that. So these, I don't know. I actually have no idea what those are. But I know that when you add the two together, you get this. Understand? Now, how is this going to be used? What I'm going to do is I'm going to take this one right here, okay? This one right here. And I'm going to subtract that integral from both sides of this equation. I mean, it's an equation, so I can move things around with addition and subtraction. I'm going to take this, leave it here, bring this over to the other side so it looks like this. uv minus integral of u prime v plus, not plus, it's equals now, equals this. Understand? Just manipulating things algebraically. Now I'm going to do one more thing. Let's see if you can follow me on this. Because this is an equation, it doesn't matter which way I write it, right? Like if I put, x equals 4, I could put 4 equals x. It's the same thing. So I'm just going to switch the order. I'm going to put this integral on the left. And I'm also going to write the u in front of the v. And instead of writing v prime, I'm going to use a different notation. I'm going to use Leibniz notation. I'm going to write dv here to represent the derivative of v. Right? So does everyone see that's this? Equals, now the other side is this, right? So I'm going to write uv minus integral, and then here I'm going to rewrite this as v times the derivative of u, so I'm going to write du. Does anyone have a question on where this came from? Started with the product rule, integrated both sides, then everything was just algebra after that? And that's it. That's the integration by parts formula, but you look at it and you're like, so what? You know, like, what does this do? Are you raising your hand?
Yeah.
Yes.
I just have a question. When you moved over the v integral v prime u, wouldn't it be negative?
Yeah, it was. It's right here.
Oh, okay.
Yep.
Oh, okay.
Right. I moved it over so it became minus.
Oh, okay.
And then when I changed the order of these, I didn't switch sides. I just rewrote it. Okay. Equality doesn't matter which way you write it.
I see what you mean.
Okay? All right. This is so fundamental. I can still remember Dr. Richardson trying to just drill this into my head when I was a student in this class. And he went on to teach me a lot of things in mathematics that now that I look back at this, it's like this is the one thing I want students to take from this formula. And if I can get it across like he did, then it's a good thing. So hopefully this will work. All right. We start with an integral, right? Within this integral, we have u, which we said was a function of x, right? So you just have some function of x sitting here. And then next to it, you don't have a function. I mean, it's a function of x, but it's actually the derivative of something, right? So this would be the derivative of some function. I'm going to call it g. So you've got this integral. You've got some function of x times some other function, but it actually is the derivative of something. Sitting together in an integral, and you're sitting there and you're scratching your head and you're going, I have no idea how to do this, right? Well, it turns out, according to this formula, that what you need to do to figure out this answer is just do the u times the v, which would mean this function, f, right? F of x. What would v be? It would be the antiderivative of g, right? Because if dv is g prime, then g would be v. So this would be g of x. Understand? Minus a new integral. Now this new integral is what? What's v? It's g of x. And then what's du? It's the derivative of which function? F of x. Okay, so let's really try and focus on what the hell this is allowing us to do. We start with something, we're scratching our heads, we have no idea how to do it. This formula allows us to transform this derivative, this integral, into a new integral with some junk in front, right? But this new integral is different than the original one. In which way? How is it different? Instead of, it's backwards. Instead of f here, what am I going to have over here? Its derivative. And instead of the derivative of g, what do I have over here? Its antiderivative. And the hope is that this integral is easier than this integral. What we've done, though, is we've transferred the derivative. Here, f did not have a derivative. In the new integral, it does. Here, the g does have the derivative, or is the derivative of g. Here, it is not the derivative. So you see the derivative switch places, and that's what I can remember Dr. Richardson saying, is that the integration by parts, IBP is what I call it up in the notes, is transferring of the derivative. That is the beauty of the formula. You transfer the derivative over from one function to the other. Now, a way to remember this formula, because it's hard at first to remember it, is a little saying. Where is it? There it is. Ultraviolet minus voodoo. It's one of these things that once you hear that the first couple of times, you'll never forget it. Ultraviolet minus voodoo. So it comes from this. Ultraviolet minus voodoo, right? Voodoo. You have to remember the integral sign, okay? But if you kind of get that hardwired, I've remembered that ever since I was told the first time, right? So you use ultraviolet minus voodoo. I have just 5 minutes. I want to show you one example of integration by parts. And we're going to do a simple example. And this is a good example because you can't do this any other way than integration by parts. There's no other way to do it. Well, you can do it numerically with Chapter 8 later on, but we're not there yet. All right, so let's run through a couple of things here. You can't use the power rule, right? You can't split this into two integrals, right? Because it's a product. So you can't say, oh yeah, the antiderivative of x is 1/2 x squared and the antiderivative of sine is negative cosine. We talked about that last class. That Cal 2 would be too easy if that's the way it was. So we're trying to undo the product. How about a basic substitution, which is what most of today was about? Do you see something and its derivative? I see x and then its derivative is 1, but we said don't you do that. What are your only other choices, really? Sine x as your u? Do you see its derivative there? Cosine x? So you can attack this with basic substitution all day long. Nothing's going to happen. Instead, though, let's try and attack it with integration by parts. So the thing about integration by parts is you have to make a choice. You have to look at your function, your integrand and everything here, and you have to make a choice. What is going to be your u and what is going to be your v prime? Right? The formula looks like this. Integral uv prime equals uv ultraviolet minus v du, which is that, right? So something there has got to be your u, and something else has to be your v prime. So let's look at our options. What's one thing I could choose for u here?
X.
I could choose yet x to be our u, right? So I'm going to make a list of possibilities. I could let u be my x. In that case, what would my v prime be? And what would my dv have to be if I choose my u to be x? I think I like this formula written a little different. Hold on, let me do it this way. dv du, okay? That's a v. Okay, if you come in here and you say that's going to be my u, what's the dv? What's not?
Cosine u.
No. It's everything else that's there. You don't do any derivatives or anything. See, we're going to say one of these, this piece right here is the u, right? That means everything else has to be the dv. So dv would have to be the sine x and the dx. Understand? That's one thing I could do. What's another possibility I could have used? Or I could have chosen for my u the what? The sine x, which would then force me to use x dx, the only things that are left, as my dv. Can anybody tell me which one of these? Well, is there another possibility? I mean, I chose this for u once, and I chose that u for once. You don't ever choose dx to be your u. Okay, that you just never do. So, which one of these should I use? What did I tell you integration by parts is? It's the That's right, the new integral, right? But we are going to transfer the derivative, right? Transfer the derivative. So what we know is that if I do it this way, in my new integral, I'm foreseeing, I'm looking into the future. In my new integral, instead of working with u, I'm going to be working with what? The derivative of it. What's the derivative of x? 1. And then here, instead of working with dv, my new integral will have what in it? The antiderivative of this, which would be negative cosine x. So my new integral is going to have a 1 and a cosine in it, which is just cosine. Isn't that a nice integral? Versus this one. Now if I do this, what is my u going to turn into in the new integral? Cosine x, that's fine. But here, dv is going to become v, and that means I need the antiderivative of this. And what's the antiderivative of this going to be in the new integral? 1/2 x squared. So what would you rather have? Would you rather have a 1 and a cosine, negative cosine, or would you rather have a cosine and a 1/2 x squared? The first one, right? So this one is a poor choice, and actually integration by parts won't work if you choose that one. Understand? Do you kind of see this? I have to finish it. I'm out of time though. So should I just leave that as an open thing, or should I finish it? You want to finish it? Okay. So different instructors have different ways of doing this. This is the way I do it. If you don't like it, find your own way. I always just make a table, and I always write down u here and dv here. These are the things I will have to identify every time I do integration by parts. I have to identify what my u is, what my dv is. U for us, we said the best choice was x. In dv, we were forced to use sine x dx, right? Yes? All right, now from here, the reason I wrote this table like this is because in my new formula, I'm going to need the opposite of these. So in my new formula, I need the derivative of u, which would be the derivative of x, which is 1 dx. Don't forget the dx. Right? 1 dx. And then here, in my table, I have to go up in the table, which means antiderivative. What's the antiderivative of v? Antiderivative of v is going to be v. Negative cosine x, right? No dx. So do y'all see that the step from here is actually an integral? You have to do the integral of this and go up to here. And now we plug in the formula. This, according to my formula, this will turn into ultraviolet minus voodoo. So what's ultraviolet? U and V, right? Ultraviolet. Multiply those two together. What is it? X times this, negative x cosine x, minus integral voodoo. And voodoo is going to be this diagonal right here. Voodoo is this times this. So negative cosine x dx. The minus can come out and become a plus, right? So I have negative x cosine x plus integral cosine x dx. And now it's time to find the antiderivative of cosine, which is an easy one to do, right? It's just sine. So our answer is negative x cosine x, then what? Plus sine x, and then plus Christy, right?
Yes.
All right. Plus Christy. That's it. That's the antiderivative. We will definitely have to do a lot of examples of this. And I don't want to give you any homework from this because I want you to focus on substitution. You're free to pack up and go. While you're doing that, I'm going to take the derivative of this to prove that it is correct. So I'm going to do product rule here. Derivative of this is negative 1 times cosine x. Product rule plus derivative cosine, which is negative sine x, times the first one, which is negative x. And then plus, now derivative of sine x is cosine x. And so when I put these together, it should work. These cosines cancel, and then this is a negative x, and then here's a negative. I bring it in front. That's positive x sine x. And that is that was the integrand. Okay. Have a good weekend. We meet again on Tuesday, right? So we don't get that holiday. Monday is a holiday, though. All right.